Hi, everyone. My name is Ian Lake.
And my name is Marcello Galhardo.
And we're here to talk to you about Navigation3, our compose-first navigation library. We'll go through some of the basics, then dive into the internals of NavDisplay to figure out exactly what it's doing.
More important, we will talk through each layer of Navi3, starting with our humble backstack, going through the Decorator APIs used for saving state, the Scenes API for customizing how screens are displayed, and how you can hook into the predictive back APIs to really take your app to the next level.
Now, if you don't know what all those things are, that's OK. You're in the right place. We'll go through all of them, but to really make sure to take the most out of our time together, we'll make sure we're all on the same page of what Navigation3 is all about. Like I said, Navigation3 is built from the ground up for Compose. When you think about Compose APIs, there's usually two pieces, a state and something that uses that state. In Navigation3, that state is the backstack of your app. The whole point of a navigation library is moving between screens in your app. If you only had one screen, you probably wouldn't need to be here. In Navigation3, the backstack contains the keys that uniquely define the identity of each screen in your app. Once you have your backstack, Navigation3 offers a NavDisplay component, which takes in the backstack and it handles actually displaying the content associated with the keys on your backstack. So if we look at this in code form, this is a complete working Navigation3 solution. So this is all the code that you'd actually need to write to get Nav3 working. So you start off defining the objects that represent, in this case, our home screen. It extends our nav key interface, you can see here, which lets us use our remember nav backstack helper method. This is what is owning the backstack. And we pass that backstack to NavDisplay to actually display what we want. The entry provider, DSL here, ties our keys on the backstack, like that home data object, to the actual composable content we want to display, in this case, just a hello world. The important part is that you own the backstack. Whatever logic you want to do to control who or when you change the backstack is up to you. In fact, the NavDisplay doesn't care about where the backstack is defined. It'll take any list of any from any object and from any layer of your app. It doesn't need to be in composition here. So the first question when we're trying to understand this code is, all right, what is this remember nav backstack doing? Why do we even need this nav key? So for that, I'll hand off to Marcello.
To understand what remember nav backstack is doing, let's start with the simplest compose code and explore the issues we came across. The very simplest backstack you could want is a list of any. But because this is compose, you probably want something that automatically triggers recomposition when you add, remove, or change the list. So you probably actually want a snapshot state list. All of the rest of the layers of Navi3 work with any kind of backstack, with any kind of object making up the keys on the backstack. If you want to have your backstack be a JSON encoded string synced across every device the user has ever logged in, Navi3 isn't going to get in your way. We might question a bit your sanity, though. But when we are going through our initial explorations on the backstack, even this code had some serious problems. Namely, unless you're an expert in Compose, this might not be the most obvious code to write. You might not even know what snapshot state list is. But more important, this isn't savable. When you use remember, the value is saved across recompositions. But if the code ever leaves composition, whether that is due to configuration change on Android, process death, and recreation, or just being a horizontal pager or any other lazy container, the value resets entirely, leading to a bad user experience. If we just replace remember with remember savable, we have made a huge promise that our any is actually a savable type, which effectively forces it to be a primitive type or pull in Android-only concepts like Java serializable or parcelable. This is fine if you're happy with just using strings, but we knew we could do better here. If you were here last year, you might remember that we talked about our efforts to adapt save state to KMP. Since then, we have gone stable and provide first-class integration between save state and Kotlin acceleration via the Remember serializable APIs, which get us a lot closer to our goal. A Kotlin multi-platform friendly API that supports and restores rich type-safe objects without relying on concepts like parcelable. Kotlin serialization works by using the appropriated key serializer to help construct the serializable object out of individual fields. But when using a list of any, it gets very confusing how exactly you trace back the correct serializer. Your type has essentially thrown away important information that Kotlin serialization was depending on. So, while you could use a list of any, we would really recommend against it. Instead, if you want to use type-safe classes with Kotlin serialization, for the entries on the backstack, we built a thin wrapper around the snapshot state list called NavBackstack. It sets up the right key serializer for serializable classes that implement our marker interface, the nav key. That is still a lot to type, so we did what most Compose APIs do, and we added a remember method that does the remembering for you. If you are on Android, that's all you need to do. Define your backstack entries with serializable objects or classes that extend nav key, and add them to your backstack. But this only works on Android because we are cheating a lot here. We actually use reflection to do this logic. The Android key serializer for nav key embeds the class name into the encode save state. So when we decode it, we can use reflection to create an instance of the class and grab the right serializer for it. For other platforms, Kotlin serialization requires a bit of additional information to find the right serializer. While previously, Kotlin serialization required manually telling about every possible subclass, the 1.10 release introduced the ability to register all subclasses of a sealed interface in a single line. So we recommend that each module in your app use a sealed type for its nav keys. Then you can pass these through the serializers module of the saved state configuration you pass to the remember nav backstack function. Each additional module would require adding its sealed interface to the configuration. This ensures that Kotlin serialization has all of the information necessary to save the backstack and reconstruct the backstack when it's restored.
Finding that right balance between verbose and type-safe is tricky, particularly when that helper needs to work on every platform supported by CMP. But a backstack is just a state. We still need that component to actually do something with that state. That's where NavDisplay comes in. So connecting our backstack to NavDisplay is as easy as just passing it through. The NavBackstack class implements the list interface, which is all NavDisplay really needs. That's why we call Remember NavBackstack a helper. You can actually do everything, get everything working without it, but you'll be taking on more responsibility yourself. But our serializable key isn't composable content, right? That's really what we want to display on the screen. So that's where the only other required parameter for NavDisplay comes in, which is that entry provider. Entry provider sounds a little scary. I might have DI flashbacks. But it's really just a map from the key in your backstack to composable content. And that composable content is tied into what we call a NavEntry class, which is why it's called entry here. We have this little DSL that makes it easy to do when you're using the serializable classes that NavBackstack uses. But it's really just a fancy statement for decoupling your stateless screens from navigation. So tasks like hooking up that DI system to grab dependencies would all happen in these entry provider scoped extension methods that you'd want to co-locate in the modules with those stateless screens. So our full solution might look like constructing our backstack, then passing that into our NavDisplay along with an entry provider that pulls in those extension methods from the various modules, right? There's a lot of flexibility here, so if you want to go crazy with your DI system and like inject entry provider scope, that's totally fine, but that complexity is on you, it's not on us. Similar to Remember Nav Backstack, though, these few lines of code are doing a lot of heavy lifting. The actual set of parameters that you can pass to NavDisplay is it's a lot larger. Thankfully, we still have a half hour. So to understand what all these things are doing, we're going to need to dive a little deeper into NavDisplay. Now, I don't know about you, but when I try and figure out, OK, what is this doing, I really enjoy that ability of just like clicking into the code and seeing what's it actually doing under the hood. So let's do that together. And OK, the first line, it's just checking to make sure the backstack's not empty. That makes sense. That's probably a lot better than just having a blank screen for our users. Next, it's constructing a list of nav entries using this remember decorated nav entries method. So I see here's where our backstack is being passed through here. But it's also passing that entry provider. All right, I know what those two things are. We've talked about those. But also passing this entry decorators. Right? And then it just calls another overload of NavDisplay with that list of entries and, well, all those other parameters we haven't gotten to yet. So this remember decorated nav entries must be doing some heavy lifting for NavDisplay. To understand what it's doing, we have to look at what those decorators are doing. So we had talked about entry provider just being a way to tie keys on the backstack to composable content, which means an undecorated nav entry is just a map method. It's just calling your entry provider and invoking it with the given key. Remember, it's just a lambda, right? So the actual complexity here is in decorating those entries. So let's first start with the term decorating. So a decorator pattern is really all about adding additional functionality in a way that it's transparent to all other layers of the system. So the simplest decorator wouldn't actually do any decoration at all. It would just display the content of the entry directly. But even this structure is really useful. For example, you could extend this pattern to adding analytics code to every screen of your app by just writing your analytics code of choice just once in a decorator. Here we use the lifecycle start effect to track how long users have spent on a given screen, using the content key of the entry as the identity of the screen. This idea of using the content key of the entry as its identity is one of the key controls you have as a user of Navigation3 over how all decorators work, particularly when it comes to the other half of the Decorator API, the onPop callback. You'll note here we give you that same content key back in the onPop. This is the indicator that every entry with that content key has been popped off the backstack and that every one of those entries has fully left composition, having finished all of the exit transitions they have. So this is your opportunity to kind of clean up anything. So for example, this is exactly the kind of information you'd need to create decorators that save state on a per content key level. So on our NavDisplay definition, we only add one decorator by default, which is the savable state holder nav entry decorator, right? Which you can imagine works with savable state. So this is the one that actually is making sure that like remember savable or remember serializable works within each screen, and that that state gets saved and restored as you swap between screens. Now, keeping track of every entry's save state feels like a daunting task, but when we fill in the decorator's implementation, it's actually just 2 lines of code. One to set up the savable state provider around each entry's content, and the other one to remove that state once it's popped off the backstack. Nav3 is taking care of all the bookkeeping and tracking of which entries are in the backstack and which are in composition. That is the logic that remember decorated nav entries is doing for you. So if we split that logic out of NavDisplay, we now have 3 pieces. Our backstack, our decorated entries, where now our backstack and our entry provider are now provided here, and then our NavDisplay, which is just taking that list of entries. Now, you'll note here, NavDisplay also needs one other parameter now. It now requires an on-back lambda. So when you pop the backstack, this is what's actually going to be called by NavDisplay's internal handling of system back, right? When you do that predictive back animation on Android or even on iOS, right? This is what's going to call it. Because remember, you own the backstack. So we can't update it for you, right? So you need to tell us how to pop your backstack. Now, everything works here as before. As you add keys to your backstack, entries get created and decorated and have state associated with each screen, which then gets passed to the NavDisplay. Now, when you remove a key from the backstack, the on-pop of the decorators gets called, and the state associated with that content key is removed. The real power we've unlocked by dropping down to this layer is that we can now create multiple lists of decorated entries with multiple backstacks, each with its own set of decorators, and with that, their own set of state. In the single list of decorated entries case, right, when we're not using this layer, swapping between one backstack and another from our home backstack to our chat backstack is actually going to destroy all of the state of the one that you just removed, right? Because from Nav3's perspective, all you did is just pop everything off the backstack and then add a whole bunch of new entries which have different content keys. But if we use two calls to remember decorated nav entries, a separate one for the home entries and a separate one for the chat entries, now when we swap between them, they're completely independent from one another. And we save the state of each stack independently. So on pop is only going to be called when you actually pop something off one of those two backstacks.
We see the entries and on back we just talked about. Oh. Sorry. Now that we have split the entries and the entry decorators out of the NavDisplay, let's take a look at what our NavDisplay has for parameters. The entries and on back we just talked about, but to figure out the rest, we will need to dive deeper into NavDisplay. Just like we did before, if you want to figure out what is going on inside, we will click into it to see what exactly it is doing. Let's go line by line together. We have the same kind of check for an empty back. Then it is creating a scene state object, passing in the entries and the on-back lambda into it, which we are already now very familiar with, along with a list of scene strategies, a list of scene decorator strategies, and a shared transition scope. Next, it has a section on predictive back handling. Ian had mentioned that NavDisplay handles the system back gesture for you, so that's probably how it does. And then it just passes that newly constructed scene state and the navigation event state into yet another NavDisplay overload. To understand what's going on here, we will need to dive deep into the next big feature of Navigation3, scenes. If you think about your app running on a phone, you might split it into two categories: the content itself and the Chrome or scaffolding around it. Think top app bars or a bottom navigation bar. Now, when your app is small, it might be tempting to put all of the content inside your NavDisplay and put all of the scaffolding outside of NavDisplay as a global UI, let's say, defining your activity. I do see that's very frustrating, and this can lead to a lot of problems. And there are very few apps that really have global UI that is always there. You probably don't want your bottom navigation bar to be on the screen when the user is logging in for the first time, or when you go to a full screen image viewer. This is really an example of conditional shared UI. And global top app bars fall apart quickly when you consider that titles, actions, and hero images are really all entry-owned state. They aren't global. So the entry-owned shared UI really needs to be part of the entry itself. This entry is contained within what we call a scene. The default scene is called single pane scene. And this conditional shared UI, these are the scene decorators that are passed into our remember scene state. These decorators wrap the scene while still being part of the NavDisplay. This ensures that when you navigate to that full screen image gallery, the bottom nav smoothly animates with the rest of the scene. Similarly, when you finish the login case, the bottom nav is smoothly animated in with your home screen with one single transition. That sounds complicated, but let's go through the implementation to see how that works. Starting with single pane scene, you will see it doesn't actually need to do much. It takes in a single nav entry, and then the content method just called entry.content. You will note that there is an entry property which returns a list of entries. A lot of this interaction between a scene and entries is about this one-to-many relationships, which is very important to more complicated scenes. But NavDisplay didn't take a list of scenes. It took a list of scene strategies. Scene strategies determine when a particular scene should be used. Each scene strategy you pass in is asked in order to whether it wants to handle the entries that were passed to NavDisplay. If a scene strategy returns null, the next scene has a chance to continue. Since single pane scene is the default, you don't even need to pass it into NavDisplay. It will automatically be the last scene in the list and override the calculate scene method to always return a single pane scene. The entry is displayed, is always the last one in the list. And the previous entry is everything in the list except the entry being displayed. This line is quite important to get right, since this is what controls the scene that we'll display during predictive back. We run through the list again to calculate the previous scene so that we know what to go back to. Finally, each scene has a key. NavDisplay uses an animated content under the hood, so this key changing is what triggers the animated content to animate between the two scenes. If the key remains the same, animated content doesn't run an animation, and predictive back is up to the scene itself to handle. Single pane scene is a default for every kind of device and every kind of entry. So it unconditionally returns a no-null scene. For Wear OS integration with Navigation3, it works very similarly by always returning their custom scene, ensuring that you get the right watch-specific transitions out of the box. However, when writing a custom scene, you should take into account both the device state and the entries when deciding if your scene strategy should return a scene or return now to continue to the next scene strategy. For example, Material 3 offers a list detail scene strategy that allows you to opt your entries into being displayed side by side on large devices. Our Navigation3 recipes has a simple example of this conditional behavior in the two-pane scene strategy. It uses the window size class of the device to only apply the scene when there is enough space for two panes side by side. These external signals are read once when creating your scene strategy, and then used in the calculate scene method. Calculate scene needs to be fast and stateless, so we want to read this value just once outside of the calculate scene method. The other option for conditional behavior is looking at the entries themselves. In addition to the composable lambda representing the content of the entry, you can also attach metadata to the entry. The key value pair is how you set custom transitions for your entry, but it is also how you opt into a given scene. So in addition to writing the strategy, your scene also contains a type-safe metadata builder, which lets developer using your scene opt in with just a single line. Internally, this is really just a helper method that uses our metadata Kotlin DSL, which enforces type-safe by tying your nav metadata key to the value you want. Here is just a simple Boolean example, but your method could take a bunch of parameters and wrap those in a data class, for instance. Then our calculate scene can read that metadata to determine whether it needs to take over. Again, opt-in is the way to go, so our scenes check to make sure that both of the entries it plans to display have opt-in to be displayed side by side. This ensures that you can always add a new scene strategy without changing the behavior of your app. It allows you to A/B test adding in the metadata or not. So by adding scenes, our single-pane layout on phones can become a multi-pane scenes on large devices. This layering lets you reuse the same entries for different configurations, picking what makes most sense for your app, whether that is a list detail layout or maybe a dialog or bottom sheet. But we want to give the same flexibility to the conditional shared UI, the UI that sits outside of the scene, but still within the NavDisplay. We recommend implementing these patterns using the scene decorators. To implement a scene decorator, you create a scene decorator strategy. For example, if you want a bottom bar to be presented only on a subset of screens of your app, you implement the one method of the interface, decorate scene. Decorate scene is then passed in the scene generated from the scene strategy. And just like how we check the entries metadata, we can check the scenes metadata to know whether to show the bottom bar. By default, the scenes metadata is pulled from the contained entries metadata, so this same process of adding metadata to your entry is passed through to this layer automatically. Just keep in mind that if your scene contains multiple entries, it is the metadata from the last one that gets used in the default implementation. But the implementation decorator, you may ask, it is just another scene. The decorator can do any custom layout logic or additional behavior it wants, then call scene.content to show the wrapped scene. Since a scene decorator strategy returns a scene, you can layer many of them on top of each other. They will each get applied in the order they are passed in. So, all of this logic of computing the correct scene and applying all of the scene decorators is contained within remember scene state. In addition to the entries, the scene strategies, and the scene decorator strategies, we also pass an optional shared transition scope. Just by wrapping your UI in a shared transition layout, you gain access to a shared transition scope. This is enough to enable cross-scene shared elements for entries that appear in both scenes. Here, we see the transition from a single pane scene to a list detail scene that automatically moves the list pane between the scenes. And that would include support for predictive back. The last parameter passed to remember scene state is the onBack. But every scene needs this. Not every scene needs this. But this onBack enables scenes to handle system back by reading the onBack from the scene strategy scope that the calculate scene used was its receiver scope. This enables the scene to customize its own internal predictive back animation while still sharing the same onBack logic to update your backstack. So, once all of the scene calculation is done, the scene state now gives us all of the information we need to not only know what the current scene is, but to know the entire backstack of scenes. This is an important distinction since scenes can display multiple entries like in our list detail case. That means the backstack of scenes is shorter than the backstack of entries. And one system back gesture might pop multiple entries at the same time. This connection to the system back happened via the Navigation event APIs. The Navigation event library is a multi-platform library that gives you system back on Android, iOS, and desktop through integrations with Compose multi-platform. Navigation3 offers helpers that wrap the Navigation event API that allows you to pass in the scene state directly. This builds a navigation event state instance, which lets you listen for predictive back gesture and tie those animations into your own custom components that would run synchronously with the animations of the NavDisplay that NavDisplay is doing. The navigation back handler call is what connects the navigation event state to the gesture, taking over system back only when your backstack of scenes has more than one scene. Finally, the scene state and navigation event state gets passed to the NavDisplay. These three pieces now have separated, clear responsibilities. Building the state that represents what should be displayed, integrating with system back, and the actual display of the state.
The best part about this very clear separation is that the NavDisplay is actually true to its name. It's solely about the display of your entries after they've been decorated and after they've been put in the scene, and that's been decorated, all of which the display level is blissfully unaware of. In fact, because we've moved all this logic out of NavDisplay, you could replace NavDisplay with just a simple box around the current scene. All the scoping provided by your entry decorators still works. All the adaptive scenes that you've built still works. But clearly, NavDisplay is doing a lot more than just this box. Most of the other parameters to NavDisplay in that big list we showed are actually what's fed directly into the animated content that drives NavDisplay. So you could write something a bit more complete that uses animated content. You'll note here we use the scene key as the content key and just pass through all the other parameters. This is a lot closer to what NavDisplay does internally, but it turns out it's a bit more complicated the more closer you look at it. To actually match what NavDisplay is doing, you'd need to also add a seekable transition state that you can seek based on the progress sent from that predictive back gesture. An is-pop concept, since animated content doesn't have a differentiation between forward and backwards, it just has a target state. And you'd also need custom z-index logic that uses that is-pop logic to correctly layer scenes in the order they're in the backstack. Similarly, you'd also need a lifecycle owner wrapping every scene's content that's transition aware, ensuring that only when the animated content has finished its transition do you actually allow the lifecycle to reach the resumed state. Oh, and to support overlay scenes, such as dialogues or bottom sheets, that you live outside of the animated content. So that's a lot, but maybe just use NavDisplay, and it'll do all of this logic for you. So really the question becomes, how much do you want NavDisplay to do for you? You own the backstack, but how many of these other layers do you want full control over? If you need multiple backstacks with their own decorators and their own decorator state, use remember decorated nav entries to pull that out of NavDisplay. If you need direct access to the scene state, or you want listeners for predictive back progress, use remember scene state and pull that out of NavDisplay. But if your use case is simple, your code can be simple. As your code gets more complex, Navigation3 grows with you, giving you building blocks that mean you don't need to reinvent everything from scratch. That way, you can focus on the content of your app and not outgrowing your navigation library. Thanks all for coming to our deep dive into Navigation3 and NavDisplay. You can look through our docs at developer.android.com and check out our Nav3 recipes repository on GitHub if you want to skip straight to the code for how to approach many of the common use cases with Navigation3. We'll be here to answer any questions from the mic here, and we'll also be at the Google booth afterwards. But please remember to vote on our session. Thanks. Any questions?